All right, so I want to frame this talk in terms of AI interpretability because that's the big new thing in AI now that industry is taking over a lot of the models and making them way more successful that academia can. And so I think one of the important aspects is to try to understand these models and use them to our advantage. And I'm going to talk about two applications of how we can use AI with the interpretability to gain insights in the scientific world. So hence the title. So we understand the world around us pretty well, hopefully, but there's a lot of things still to be discovered, hopefully. For the first time, we have non-human intelligence that can help us in discovery. And there's a lot of opportunities because the models, AI models, are performing really well. So the performance is great. And you can imagine that if you pair performance that they're doing with internal causal interpretability, where you can understand what each unique part of the network is doing, or at least a subset of parts of the networks are doing, then that's has a huge potential for causal insights for any data type. Okay, so what's roughly the current landscape in AI in language, right? So we have LLMs like GPT-4 or Llama 3 and so on, and they're hugely impressive, but they're not really realistic. It's not how humans learn, okay? So to me, they test the limits of what neural computation can do, but they don't answer questions like how does artificial neural computation does X, right? And they're becoming very big, and it's very hard to do behavioral interpretability on them. Internal interpretability. It's hard to look inside them because they're so huge. There's no bottleneck. A lot of the times they're closed models to begin with. So what can you do? And so I think we need to be in parallel developing more realistic alternatives to LLMs that learn language. And that's what my lab does most of the time. And the question that I'm interested in, how properties emerge, not only what is possible in artificial neural computation, but how properties emerge, how we're similar and different, humans and artificial neural nets. And we have this ability to do internal interpretability. We can look inside the neural nets and see what's going on. So I'll try to show how all of this is useful for scientific discovery. And I'm gonna talk about basically, two use cases, one on the neuroscience side and one on animal communication. Speech is great. Speech is great. I mean, first, it's easy to get neuroimaging data on speech here, and there are several places where you can do neural data on speech. You can do it on the brainstem, and you can do it in the cortex, and that's a hugely advantage once you do comparison with the AI model. Speech is less complex than vision in some ways, in many ways. So if you're doing this general purpose vision models, they have lots of colors and lots of objects and lots of concepts, whereas spoken language has pretty much just about English 40 phonemes that you combine. And so that's easier. And interpretability, when you have something easier, that's an advantage. Humans have innate generator in spoken language, which we lack in vision. I can ask you to imagine a red apple, and you can imagine a red apple. I'm sure most of you are imagining a red apple right now, but I'm not seeing any red apple. Whereas when I say a red apple, you're all going to say red apple. You're going to say it slightly differently. So we have innate generator. When you do interpretability of generative AI, that's actually a good thing to have. So the humans actually have innate generator. And we know a thing or two about language. So that's helpful. And if you think of speech, spoken language, it is the only, it is what representation learning is all about, right? So we humans take a continuous space of sound that is measurable physical continuous property, and we learn mental representations about those sounds that cannot distinguish and carry meaning, right? So we go from continuous to representation world. And that's exactly what deep neural nets do as well. They say take some continuous, digitized representation of continuous world and represent it with some words. There's a very interesting thing going on right now in AI and language and in general, which is we want to understand whether humans are just smart, whether LLMs will ever get to human level, right?
No.
Okay, never. Good. I'm not saying that's just a thing we want to understand, right? So incidentally, that's what animal behavioral people have been trying to understand for a very long time. Are humans just smart animals, or is there something that is additionally required for us to be as smart as we are? And Chomsky's idea would be yes, there is some domain-specific, language-specific thing that we need to assume, and alternatives would be no. So if you said no, for you, then probably this is the two sides of the same debate, right? So are we just smarter? Is it just about scaling? And somewhere down the road, you get human intelligence as you increase scaling, or is there some specific things? And likewise, as we're going to scale LLMs, will they ever get to? Okay, the first step I mentioned to try to understand these models is to make them more realistic. And actually, that's super useful for when we want to do modeling of language and modeling of humans. So LLMs as a cognitive model are not that great because they learn from only text. They learn from enormous amounts of text. So no baby learns like that. No baby learns without listening and hearing, again, raw audio. And no baby learns without communicative intent. So how do people learn? I don't think that I need to tell this here, but it's useful to think about this in terms of this old scheme, which is I have some information. I move my mouth so that the air coming out of my mouth as the sound coming out of my mouth carries that information into your ears and into my ears, my own ears. Your vibration in your ear get transferred into your signal, and you decode that information. Hopefully, my information, your information match, and we've communicated. So this is what we've built so far, step by step. Hopefully the most realistic model of human language learning using exclusively deep neural nets. Okay, so how does this work? So we have a couple of components. One of the important components is the generator, okay, the thing that produces sound. It takes some information and it takes some random errors, but very few numbers. It takes a vector of 100. Of that 100, a couple of variables are, just information in theoretic terms, right? So just a code, a binary code or one hot code. And what it does is through a series of convolutional layers, it produces EMMA movements. So EMMA is a way to measure articulation. Okay, so we need to talk about EMMA.
What does it stand for?
Oh, electromagnetic articulography. You put a bunch of electrodes on people's tongue, lips, and teeth, and then measure how they speak. Okay, so you have 3 points on the tongue, 2 points on the lips, 1 lower incisor, and you have X and Y. And you're recording how people speak. Okay, so our models are generating these virtual mouth movements. And then a pre-trained physical model takes these mouth movements and turns them into sound. Now, that sound travels first into the discriminator. So this is a GAN-based architecture. I don't know if you've heard about GANs, but they were popular at the beginning of picture writing. They were creating faces of people that don't exist, but you wouldn't tell. You couldn't tell them. It's an extremely powerful and interesting architecture because it's the only architecture where this guy never sees the data. So it's not replicating data, but it's imitating data. So how is it imitating data? It needs to learn to produce speech through mouth such that another network will be unable to distinguish what is real and what is fake. So this guy gets real data. So you can imagine this parents out inputs, and it gets internal real fake data or generated data and needs to distinguish. So at the beginning, of course, this guy's very good because it's easy to distinguish noise from real speech, and this guy doesn't know how to produce speech yet. Over training, of course, this one starts to approximate the language of the environment so that this one will not be able to distinguish. So this relationship is imitation learning. Okay? Now, that's not always, we're not just imitating, right? We're actually, sometimes I talk about our language as informative imitation, because we're encoding information into spoken language, right? So what this guy also do is it needs to create speech so that this speech carries information. Because this sound gets also sent to this network, and this network needs to guess what unique code was here in the latent space. Okay, so it's encoding, decoding, it's production, perception, right? And then this guy in training becomes a really good classifier. Right? This guy, you can feed it non-generated data and they'll be able to classify data into words.
So,
Yeah.
so both of these, so each of these things are separately affecting your articulator generator circuit down there.
Yeah,
Like you've got some learning rule that's got both.
here is a pass from this one, right? It needs to learn to, it gets a feedback whether this one was successful.
And it's doing this in parallel.
Well, it's not in parallel. It's like one update.
Or I see in serial.
Serial, yes.
Yeah. Okay.
And then here you have, again, internally, this one internally gets a loop as well. This one gets a loop, and here's another loop.
All right, thanks.
So actually now we're adding a parent here. This is even more realistic. We're adding vision. It's not that preprint is not out yet there yet. But, we're trying to make it as realistic as possible. Now, note that there's nothing that forces any learning here, and there's no, like, these models learn words, but there's nothing that it forces it to learn words. All it gets is raw audio, sliced for 1 second. But that's the only supervision, no supervision whatsoever. So the network, you can give the network a bunch of codes and a bunch of words here, right? And the network could learn to encode anything about speech into, pair these codes with anything about in speech. It could, learn that 10 is female and 01 is male, or it could learn that 10 is long and 01 is short. But it doesn't do that because that's not the most informative. So it learns words, for example, just because that's the most informative thing. It learns to pair unique codes with unique words and so on. And there's a lot it can do in terms of learning.
One real quick question. So that training data is kind of matched to the latent space code. So
No, it doesn't have to be. Even if there's a mismatch, that's a great question. Let's say you have 8 words and 10 codes. There'll still be learning happening. But yeah, it helps if it's like somewhat matched, if there's some priors. It's fully unsupervised. It's learning by imitation and imagination. It is extremely innovative. So the generator, the one that generates data, never sees the data directly, which is extremely powerful. It needs to basically learn internally to construct itself to produce data without seeing the data, which is really, really powerful because they learn in a more powerful way than a model that just learns to copy. And they are able to extract meaningful information better. We have embodiment, we have communicative intent. Again, we're adding a parent, so now the child, again, is going to learn with a pre-trained parent in a reference game and so on. And we've shown in several ways how these models are developmentally similar. And the nice thing is that these are all convolutional neural nets, which for this group is good because they're more plausible from a brain perspective than transformers. And there are many things we can model, and I have a bunch of paper on how to model articulation, syntax, semantics, learning, and so on. So now we want to understand it internally. Okay, we want to understand how these models learn things. I'm going to be showing you later that they learn, lots of processes in language. For example, let's skip ahead a little. Well, no, let's go to except we don't want to just have a learner. We want to have a learner that we understand. That's crucial, and that's how we got the decoding with communication. So as I mentioned, the network takes a few variables and generates data through a series of convolutional layers. And you can identify unique units in that latent space out of 100. You can identify which variables represent what. And then there's this really powerful technique where you just take the entire latent space and take a single neuron in a single variable, a single unit in that latent space out of 100 and stretch it to extreme values. And that gives you a causal relationship of something that is important in language and the latent space, right? So the network now has internally represented what we linguists or cognitive scientists think is meaningful as a single unit in the very, very last layer.
Yeah, the Zoom controls are kind of obscuring some of your slides on the.
Oh, yeah, okay.
Maybe hide floating meeting controls. You click on the three dots. Hide floating meeting controls.
Oh.
And then you can also move that other thing, smaller.
So you can find a single variable that represents an S and take it out of the output. Or something more complex, like a morphophonological process that is copying, which is the most difficult computational thing you can do in morphophonology.
Secure.
Okay, this is going to be important when we do whales and causal inference. Okay. And it learns words as well, really well. Words, categorically. So each code becomes a unique word. So the idea is information gets encoded into words. And it learns to say new words. It learns to say start, although start was never part of training data. So I trained the network on 8 words: ask, carry, dark, greasy, like, suit, water, ear, none of which are start. But only on these 8 words, it learned enough about English phonotactics that it started saying start or sart or dust, new words that are words of English. That was kind of surprising. We're training this model, and I have an external person transcribing the outputs, and she was starting just transcribing new words, and I was like, "What's happening? These words were not part of training data." So only based on 8 words, it was able to learn enough to start producing new plausible English words.
Is it because there's some combination of the words that it heard?
It didn't hear S and T, but start is probably something along the lines of adding an S to dark and then changing K to T. So yeah, there is some of that. It also says sart or dust. And dust is, I don't know, what is dust? Dark. Yeah, I mean, it's pretty good.
But how many words did it generate that don't sound like is
Very
that
few.
it isn't like you're getting a few that it jumps out because it sounds like an English word, but there's a bunch of other garbled sounds.
No, the garbled sounds are there, but they're very, very rare. And most of the time it's words that exist. But that's basically a face that is a possible human face.
I'm just curious. Yeah.
And so the nice thing is that you can play now with this. You can basically work test these models, right? So you can train out something and then switch two processes in and out and see what will happen and see whether it regenerates on new vocabulary and so on, and it does. And actually, it has several similar steps. You can train these models and see how they're being trained, and you can compare that to human language acquisition data. So that's kind of nice. Okay. And yeah, there are other labs started using this, which I was very happy about because it's always nice if somebody replicates a result. But the good thing is that they found that, for example, English nasalization is learned differently in this study than French nasalization, which is really nice because in English nasalization is not contrastive.
Wait, what's the word? I can't understand what you're saying. What is it?
Nasalization.
Nasal.
Right? So nasal vowels.
Oh, nasal
In
is
French.
Hey, thanks. Thank you.
Yes. In French, right, you say nasal vowels, and you get there's a difference in meaning. Bon versus bon, and in English it isn't. So the models learn that, and they also learn to move their articulators in a very similar way. So this is, for example, you have these same loops for upper lip that it learns when it says a word suit and so on. So you can also study these models now as how they articulate, not just how they produce speech out of the blue, but how they move their articulators and so on. And well, there's also compositionality in how they're learned, right? So binary codes are compositional and words are compositional. So they learn, say, they have this kind of binary, each binary code represents a word, but individual bits represent subword, sublexical structure. So it learns things compositionally. Okay, so now we're getting towards the brain part. The nice thing about CNNs that they're not as black boxy as other, well, transformers at least. And this is how a generator looks like. Okay, so it takes 100 variables through a series of convolutional layers. Now we can look inside those
Like the convolution, is the convolution over time? Is that how it's convolutional about it? It's like there's not an image here, so like.
No, there is. Well, yeah, in the time domain, yeah, it's convolution in time domain. So it's a time domain. It's a time series, and then it has a monodimensional filter, and that filter produces a feature map. And if you can plot those feature map like this, okay, so x-axis tells you how many feature maps are there, and y-axis tells you how many points are there. Yes, exactly. And so if you just substack each of these feature maps, you don't get very interpretable results. But something that we started noticing that is actually very interesting is that when you summarize in the time domain across all feature maps, you get a very interpretable time series for each layer. And that's great. Because it shows, okay, green is output, purple is the first convolutional layer behind the output, orange is the layer before that, and so on. So you can see what each layer is encoding as this kind of frequency following response. So you see that this will lead to auditory brainstem response pretty quickly. So this is, for example, fricative, right? You see frication noise. But you can see it for a vowel, right? The first convolution layer before the output has a lot of information. But the more, the farther you go up, the deeper you go in the network, the more abstract it becomes. And there's a really nice way to visualize this to understand what each layer is encoding. Okay, this is now output that becomes a disyllabic word, right? So you see there's one syllable here, one syllable here, right? So same as we were forcing piru to pipiru, right? So we're forcing piru to pipiru, and it becomes a disyllabic word. Is this clear? This is waveform. But you can see how this gets constructed inside the network by looking at each layer, right? So this is layer before that. You see there's still a lot encoding, right? You have silences for consonants, you have peaks for vowels, and it gets more and more abstract, more and more abstract.
So what's the purple curve? That's
No, that's a little complex. So that's So this is the value of the variable that says whether you're a monosyllabic, unreduplicated word.
So this isn't this isn't like deeper layers in the network.
No, this is just me forcing output to be disyllabic in a causal intervention.
I see. So this is you're generating
Yes,
sound from
yes,
this thing.
yes. But this is getting deeper, like, okay, this is deeper, and this is
I
the
see.
most abstract layer. And you see that in the most abstract layer, the envelope is pretty well encoded, right? Acoustic envelope. And so the way this networks, it generates data in a very physical way. First it creates acoustic envelope intensity, and then over layers, it adds information to that. So that's a great way then to compare how humans process spoken language in the brain. So, our auditory signal travels through the brainstem and then into the cortex. And I'm going to talk about the study we did on the brainstem. So, this is my collaborator, Christina Zhao from UW. She had this fabulous study which showed that phonological processing is already encoded in the brainstem, which is not what we expected it to be encoded. But she has shown this very convincingly. So this is a syllable ba, and she sends this to 15 Spanish and English monolingual speakers in an complex auditory brainstem response. And you can see this is brain response to the vowel ba of each individual.
It's EEG.
It's EEG, yeah. They only need four electrodes, but extremely high sampling rate. So you're catching the high frequency signal as it's passing through the brainstem. The idea is that it's so early that the cortex is not processing it yet.
Where do they? So you're pointing up here, but I assume it's down on the base of
So
the.
I think you place 2 here, 1 here, and 1 for reference, and then you need 3,000. The plate is 3,000 times the speaker because signal to noise ratio is so bad.
But how do they get brainstem out of that? Like I should know. I don't know. Actually, I've never done EEG recording, but how do they know this is brainstem?
Because it's so early. Well,
Oh, I see.
because it's so
The first signal they get, they
The first
attribute
signal they
to
get, and that's
because
why-
of time of flight of the
Correct.
vaccine. Yeah. I see.
Okay, so this is summarized. Spanish and English, right? and actually this, you can hear it. This is how a sounds in 50.
In the brain.
In the brain. Actually, sometimes you can distinguish vowels. Yeah, this is just electric activity, but like you can distinguish 2 vowels from these. It's fabulous technique for what I do, but it's a little out of date in neuroscience, as I understand.
EEG or?
No, complex auditory brainstem response.
Oh.
I think it's fabulous. And so we have several ideas for doing experiments. Okay, so now you can do something very similar in these networks. So what is EEG? It's summary of electric activity in time domain, right? So what we did in internal layers, we have this feature map that each convolutional filter is producing. If you see them like this, they're not very interpretable. But when you summarize them, just like EEG is summarizing electric activity of the brain, if we summarize this artificial activity, we get a very similar response to the sound in the brain as in our deepest layer, brainstem as in our deepest layer. Now, there's a lot of work that compares artificial neural nets and the brain these days, but they all transform signals. Okay, whenever there's saying transformer match our brain signal, is because they have the brain and they have transformer representations, and they find a linear model that predicts one from the other, and they say because it's just a linear model, there's similarity. Here, this is in raw form, no transformations at all, and you can do all sorts of experiments. The second one the second sound is how it sounds internally. We can do all sorts of experiments to see how, say, language experience modulates these responses to sounds in the brain stem and in our convolutional neural nets. And actually now we have a follow-up study that is even better than this, but it's not out yet. But so we have brainstem representations, and then we have cortical representations. So I worked with Eddie's data, and there we showed that basically in the cortex level, the electrodes of ECOG respond really well with these individual feature maps in the deeper layer. So brainstem, earlier layer, ECOG, cortex, later layer. And there's a lot, like we're looking into how sensitivity period happens, right? So with Christina, we have a proposal for a grant that says, okay, let's look at babies at 7 and 11 months, and let's look at how these models are encoding representations. Or you can have babies that listen to music and language and models that are trained on music and language to see if this kind of tonal processing is better and so on. So there's a lot of, downstream. This is interesting, but this is not what the result of this paper is, just with rhythm. If you record Spanish speakers hearing ba, they will, or English speakers hearing ba, they will hear the first, English speakers will hear the first vowel vocalic period slightly earlier than Spanish speakers because of the way English encodes ba versus pa more in the terms of VOT than Spanish. And then we replicated that in the models, something similar in the models. I'm not going to go into details. The point is that you can compare how language experience modulates brain encoding and neural network encoding. And we claim that it modulates it. Okay, now on to the whales. So we're building an all-purpose language pattern discoverer. Okay, so switching off completely off the brain. I know this is your home territory, but Bruno asked me to speak about whales as well. So whales are presumably encoding and decoding as well. And they have this interesting communication system that are called codas. So they click, 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 or click, 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 click. So they group a bunch of clicks into codas, this group of clicks, and they exchange them in conversations. So this is where the normal recording this, following them. There's click, 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 click. Our animals, and very difficult to work with. But they do that.
They're doing right during that video. I mean, that's synchronized with.
Yeah. And it's from different whales. So they are exchanging, they're in dialogues. So, and they are doing this before they hunt and when they socialize. It's not mating. It's not some sort of, I mean, it could be very well vacuous semantically, but I've never seen anything as structured and interesting in the animal kingdom.
How do they generate the clicks?
We'll get there. So for longest, this was considered to be a Morse code types communication system. And our AI model, our baby language learner, said, no, there's more to it. Okay, so this is traditionally, we thought that this is number of clicks matters and their timing, right? So whether click, 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 or click, 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 right? And these are several types of code they have. So we took our artificial baby language learner and tell it, learn to imitate this communication system and learn to encode information into this communication system, right? So learn to imitate, learn to encode information. And then we took our technique, we paired it with causal inference, we stretched these individual bits and asked the model, what kind of acoustic information did you use to transmit information as you were imitating? Yes.
Is the encoder still using these, what they're called,
No, because they don't have the same mouth as we do. It's just producing sounds.
And are the clicks in two pitches? Are they high and low?
Depends on what you mean by the pitches.
Yeah, it sounded a little bit different, so I don't.
Okay, interesting. I'll get there. Okay, so we can pair causal inference and then take each bit, stretch it, and see what will happen in the output. And pair causal inference on top of that to say that there's a real causal effect. And so our technique found that the number of clicks matters, the timing matters, which is great because that's what we thought. I mean, this is just validation. But it also said that spectral mean and spectral regularity is important. So it used spectral regularity to encode information. And at the time, we didn't know that there was anything there. And I actually gave an interview. So we went and checked, and actually we found that there are very structured and interesting patterns that are analogous to human vowels in these communication systems. So how do we say A and E? How do we say the different vowels? We say A and E. When I say an A, I open my jaw, and I say an E, I close my jaw more. Basically, I'm changing the resonant body, which is my vocal tract, right? My vocal folds are producing vibration. So I was like in this elephant communication talk, and elephants have names, but they respond to names very slowly. So it occurred to me that maybe these big animals have different timing. And so if you think of their clicks, not as clicks, but as pulses, and the same of our pulses have in the vocal tract, then you can see these spectral patterns. E. This is me saying E, and you see the difference between I and E is you can know the difference between I and E even if you don't see me, because the formant band frequency form for A they're close together, for E they're far apart. And seemingly whales do not have anything like that. It's clicks. But if you think of their timing works differently, the pattern starts appearing. So what we started doing, AI predicted, look at the spectrum, predicted spectral properties to be meaningful. And then as we started we needed extra work basically, but it directed us in the right direction. We started removing timing from them. We started treating these clicks as pulses of our vocal folds. And when you do that, the spectral, very interesting spectral patterns start appearing. And here they are. I know none of this is well seen, but there's a very discrete pattern where some codas have two spectral peaks, and some codas have a single spectral peak, just like in our vowels. And you can hear the difference with your naked.
So you mean if you plot, you're saying that you're saying.
Well, just remove timing.
Yeah.
Everything else is the same.
When you say a single spectral peak, you mean that if you smear it out between on the vertical axis, you get a unimodal versus a bimodal histogram.
So this is one formant, this is another,
Okay.
and here it's only one.
So it's frequency on the vertical axis?
Yes, correct. This is a normal spectrogram.
Okay.
You can hear it with your naked ear. This is our timing, but you can hear it. You can take a piece of paper. Spectrograms don't plot well on projectors, and we also observed that some patterns are very are like our diphthongs, where there's movement in spectral properties. Okay, so again, not ideal, but you see these patterns, and these are similar across whales. It's not just one whale. We have several females. They're all matrilineal societies. These are their names. They have funny names now. Gene, fork, fruit, tweak. Very structured across whales. Two peaks, one peak, or these kind of movements. You see these patterns where first click is very high in spectrum, and then it flattens down or goes slightly up. And there's a bimodal distribution. Some codas are flat, some codas have movement. And we correlated this with several, the way they move and stuff, to show that this is probably not something that is automatic, some artifact, but it's probably default. So how are these? Somebody asked, how is this produced? We flap our vocal folds, and then we change the resonant body. This is a case of a convergent evolution. They have phonic lips that look very similar to our vocal folds, with which they flap. And then we realize, oh, they have distal air sac. They have air sac on top of those phonic lips that they probably just change the shape of to get these different spectral patterns. This is they produce sounds here, and then they in this giant spermaceti organ, they echoes, and so you can actually even get the size from all the way from the echo. But here in the air sac, they make these probably likely informative changes in the shape that results in their vocalic pattern. By the way, in a very different vocal, they also use this to echolocate. But when they echolocate, they additionally send the signal to this junk organ that has acoustic lenses. They dive up to a kilometer deep. They shoot those clicks to hear where the squid are. And these clicks are very different from communication clicks and extremely loud, 170 decibel equivalent in air. Wow. That's why they need their giant noses. Okay, so the nice thing is that our model predicted these vowels. And this is an interview I gave for one of them. Has a lot of press attention on this project, and it's one of the kids' science magazine. And I gave this interview at a time where our model predicted the vowels, but I didn't find them yet. So it's funny because it says, "Oh, our model predicted the vowels, but we need to look into them."
Could you say again, how did your model predict the vowels?
Yes. Okay. Here it is.
Yeah.
It used individual bits to encode information with spectral means and regularity. And you can get that by, this is sigma f, right? So frequency, you can see that one bit gets, it kind of flashes out as something that encodes spectral properties as you're forcing. So it is, so the model learned to imitate codas, and it learned to embed information into those codas. We asked it, what acoustic properties did you use to embed information? And spectral means turned out to be one pretty clear, where it used one bit to encode information.
When you say one bit, is that like one?
Yes, correct.
One of those.
Yes. Yeah.
So it is the
Sorry?
is it then a bubble? Or I mean, do you just have I see.
Two types, yeah. And then whether you're flat or going up and down. And the nice thing is that just as we can have, we can have like in Mandarin, right? It can have ma, ma, and 4 different ma syllables.
Yeah.
They can have 1 + 1 + 3 coda. So click, 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 and both vowel types. So it's an orthogonal system. They manipulate the rate at which they flap, just like our tones, and they manipulate orthogonally the shape of the vocal tract, the shape of the vocal. Okay, I don't think we have time for LLMs. Just a brief stuff of what we do with LLMs is that, well, humans that's kind of important. Human in the loop is still important. Okay. AI interpretability is not at a place where, I ask the model, give me an answer, and it'll give you an answer. It's a tool that helps you shrink the hypothesis space, and the human in the researcher is still important. LLMs, going back to our roadmap, are great as well, but I think they're great in not telling us how realistically things can emerge, but what are the limits of emergence, right? What are all the possible things that can emerge? And looking from an animal communication perspective, there are a lot of people asking, what is language, and do animals have language? Well, that's kind of a wrong question. The other question is what properties of human language do other animals have? And they have many. They have symbolic reasoning, they have categorical perception, like chinchillas, for example. Chinchillas do VOT, the famous Patco studies. Many things. The one thing that they probably don't have is recursion and this kind of metalinguistic abilities. And one of the things that we're looking into is whether LLMs have recursion and whether they can analyze sentences that look already pretty complex, like the cow, the mouse that the cat that the dog painted thought sang. They have probably troubles parsing this sentence.
I would too, though.
But of all the things,
Do it.
GPT-4 was the first that can do this. And not only that, it can give you a Chomsky tree analysis of this sentence. In other sentences, like I saw the elephant with binoculars, or I fed my baby turtles, and it knows that there are two. Well, actually, it's funny. I was trying to get a picture of how I fed my baby turtles in the diffusion models. And it's very hard because pragmatically, very often eat their baby tongues. And then I was thinking a lot, and I said, "Oh, try to do this in the style of Hieronymus Bosch, which was amazing painter. And if you do that in the style of Hieronymus Bosch, you get the closest to I fed my baby, the other reading." And it can do pretty good this kind of metalinguistics. We did some work on semantics, how it can do logical analysis of sentences.
With the I fed my baby turtle.
This is using linguistic formalism to try to understand how much it internally knows about structure. And it's pretty impressive. And you can use it, you can ask it to be a linguist. So this is basically playing LLMs and asking to be a linguist and analyze these sentences. And so, because you cannot look inside it anymore. So this is about behavior or interpretability. You can ask it, was hat Hans gesagt, dass gestern gegessen hat? What did Hans say that he ate yesterday? And it knows, it knows where what is base generated and that there's movement. There's a lot of syntactic theory that it knows. You can ask it to identify recursion and add a layer. The boy who I saw a girl liked yelled my name. It recognized this as a recursive sentence and then adds layers. It adds a lot of layers. So a boy who I saw a girl that a dog that a cat chased followed. It works. I'm not processing this. Anyway, there are some problems with this. The more difficult one is to avoid memorization. So actually now you cannot evaluate these models at all. No, I mean, our graduate student is making up sentences because that's the only way to ensure that those sentences were not part of training data. That's a problem, literally. And if you, I was just at the NSF workshop, people are doing benchmarks. Benchmarks now have expiration date. And next update of LLMs, you're not going to know whether it was trained on your benchmark.
Right.
Even if you gzip it and even your password protected, it's not safe. Okay. So back to the landscape. I think LLMs definitely very cool for testing the limits. I think more realistic models can give us a lot, both on kind of neuroscience and behavioral modeling of cognition and spoken language, especially, and then the scientific discovery. And I think it's an exciting time we live in because I think we're starting to appreciate these three intelligences again. When we have humans, we have animals, and then we have machines. And I think we can mutually learn from each other. A lot of the code is online. These models are very difficult, easy to train actually. So if you're interested in running them or playing, no.